It's like, if it, no, I didn't see anything.
Because I'm trying to make a podcast today, so I'm making a podcast for my government.
Okay.
And I don't know how I'm going to execute it. That's my thing.
You'll be able to figure it out. All right. So let's get started. So we're talking about the two different ways that a velocity vector can change. Melanie, what's one way that a velocity vector or any vector can change? All right, so you could change the direction. Okay, so if I were to draw that as a picture, right, I would take, here's the first vector, right, and then I would turn it a little bit. I wouldn't stretch it or anything. I would just turn what direction it's pointed, okay? So that is one way that you could change a velocity vector. Sabrina, what's the other thing we could change about a vector? How else can I make that arrow different? So this would be changing the angle. What else can I do to it? Crystal, what else could we do to the vector? Yeah, the length. We could make it longer or shorter, right? And what is that called, the length of a vector? The magnitude, right? So I could take the magnitude and I could, let's say the vector started off this long, right? And then I could make it longer or I could make it shorter, right? What is it called? What's the special name when you take a velocity and you change it? Caitlin, what is that called when a velocity vector changes? Specifically, the rate of change of the velocity vector. It would be the slope. Natalie? It would be the acceleration. Okay? So if you take a velocity vector and you make it change direction or magnitude or both, you would need to do an acceleration. What causes accelerations to take place? Flora, what do I need to do to something to make it accelerate? Have a force, okay? So there you go, there's a little bit of review, right, from our previous unit, right? We've got these velocity vectors. If you want to change the direction they're pointed or how long they are, you need to apply a force so you get an acceleration. Today what we're going to talk about is what's called uniform circular motion. We're going to take an object and we're going to make it move in a circle, right? And we're going to need to know how to do this so we can do the analysis. So I'm going to start off with my uniform circular motion demonstration. So I have a hoop here. Which I guess you would use to do like needlepoint. It's for embroidering. I'm going to use it for physics. I have this marble here. And I'll use my video camera so everyone in the class can see what I'm doing. Okay, so again, here is my hoop. Okay. And I'm just taking the marble and I'm making it move around the hoop. Put this higher up. Okay, so again, I've got this hoop. The marble is traveling around the loop here, okay? It's traveling in a perfect circle, okay? And this is an example of what's called uniform circular motion. Now on Monday, I've got a tracker video that we're gonna analyze. So you'll see this in like slow motion. Today I just kind of want to show you so you had an idea of what I'm talking about. Okay? This is an example of uniform circular motion. We'll talk about what the circular motion, I'm sure you know what that part means. We'll talk about what I mean by uniform, okay? Okay, so uniform circular motion is when an object travels at a constant speed around a circular path. It's really important that you like underline the speed part, okay? That's a really important part. Let's get that down. Right? So again, it's traveling around the circle.
Mr. Rochella, please call A19. Mr. Rochella, call A19, please. Thank you.
At a constant speed. Which part of the velocity vector is staying the same if it's traveling at a constant speed? Melissa, which part of the velocity vector is staying the same? So we've got magnitude and direction. Which part is staying the same if the speed is constant? What do you think?
The direction.
So the direction would be the direction that the ball is traveling. So like at the bottom of the loop here, it's traveling, let's say, to the left. At the top of the loop, it's traveling to the right. So it's not the direction, it's the magnitude, right? So that just means the length of that vector stays the same the whole time, right? But the question to think about is it accelerating? So I'm not going to say yes or no yet. And so, if you want to write down what you think right now, you can do that. We're going to come back to it at the end of the class. Okay? Mm-hmm. Well, we're going to talk about specifically how the velocity vector is changing. And yes, there is some loss of speed because of friction. So we're kind of ignoring that for now, but that is certainly true. So to start off, right, I've got this circle kind of showing us the direction that the ball is traveling in. And I'm going to draw, first, I can define this thing called the period. Right? So the period is the time it takes just to go around once. Right? Kind of like a class period is how long it takes to complete one class. Right? The period is the time it takes to go around this loop once. And we usually use the capital letter T for it. Okay? Right? We also can talk about how far it travels when it does that single loop. And so if it's a circle, it's got a radius r, and the distance traveled would be 2 pi r, just the circumference of the path. So if I know how far it travels, I know how much time it takes to do it, I can write down the speed v. What would that be equal to? What would the speed be? So I would take the distance traveled and I would divide it by the period, and that'll tell me the speed. What happens to the speed if the period becomes a larger number? From me, what would happen to the speed if it took more time to go around the circle? Yeah, it would go slower, right? So if you're running a lap on a track and you run slower, it takes you more time to finish it. What about if I took the loop and I made it bigger? I made the radius bigger and kept the period the same. Sarah, what would happen to the speed then? I'm just saying about v itself. If I made r bigger, what would happen to v? Yeah, it would get bigger too, right? So as you start changing the radius and changing the period, you need a different speed in order to go around the circle. All right, so now we can start drawing some arrows that will show the velocity. Right? This is the speed. It's this number the whole time. Let's say it's 4 meters per second. It's 4 meters per second the entire time, but the velocity is changing what direction it points. Let's see if we can convince ourselves of that. So this would be the velocity vector at this moment in time when the marble is in the lower right corner here. Right? And it's drawn in a special way. It is drawn tangent. So tangent is a word you've probably heard in your math class before. Remember what tangent means in a math class setting. I'm sure you've heard it. Caitlin, what does it mean to be tangent? So yes, so there is a relationship between the tangent function and like the adjective tangent. But there's another definition for it. Metzley, what does tangent mean?
Well, because like I can't think like a specific thing, but like I just can relate it to like how I use it in my math class.
Mhm.
So it's usually like to find a slope in a circular area or curve.
Sure. What's special about a tangent line in your calculus class?
That it's because in a curved line it's much more difficult to pinpoint like the points and get a slope from that, and the tangent line is straight, so it's easier to.
Is this green line tangent?
No.
The green line is called a secant line because it touches the curve in two spots. A tangent curve touches at one point, and yes, it has the same slope as the function. So another way you can think of it is if you have a circle, the tangent line, if I start from the center of the circle and I draw a line to where I'm located, the tangent line and this radius form a 90-degree angle. That's probably the first time you saw a tangent line back in geometry, talking about lines touching circles. So the radius and this line form a 90-degree angle. All we have to know is wherever the object is located, I'm just going to draw a line that it's going in the direction the ball's traveling. You don't need fancy math to do that, right? Find where the object traveling the circle is and draw a straight line that goes out in the direction it's going. What would be different about this velocity vector if the ball was going in the opposite direction? What would change about it? Araya, what do you think would change about the velocity vector if the ball was going counterclockwise? Go the opposite way, right? How about the length? Would that change? No. So yes, if it was going the other direction, right, I would draw a line that would look like that, right? So all I'm showing is the direction it's going at that moment in time. Now here, what I've done is I've just let the ball move a little bit around the circle. And the blue line vector here represents another velocity, right? As it moves around the circle, the velocity vector stays the same length but points in a different direction, okay? Did the velocity change? Yes. Remy, what changed about the velocity? The direction. What stayed the same? The magnitude. Does that still count as acceleration? Yes. Either the direction or the magnitude or both, any of that combination changes, we did accelerate. That throws people off. They think it's a uniform speed. What do you mean it's accelerating? It's always going 4 meters per second. It's the direction piece that's important. This little change in the vector here tells us that we're accelerating. Now, I'm not going to go into the specific details about doing the subtraction and then like doing the calculate, like all these little things that would tell you exactly the direction the acceleration is. We're going to come at it in a different direction, all right? So 100% yes, the velocity changed because the direction changed. That means we accelerated. So let's take a step back. Actually, let me hold on. Let's take a step back and think about the forces going on between the marble and the hoop. So at this moment in time, the marble, right, just to remind you, right, the marble is going around the hoop, right? What is the marble in contact with? When it's going around the hoop, what's one force acting on the marble? Right, so there's friction from the table. That would be sort of in the horizontal direction. That's not gonna change this velocity. What other forces are acting on the marble, Natalie? Its weight. What direction is that point? Down. So from the perspective of this picture, it points in. All right. Is that going to change this vector left, right? No. All right. So it's not friction that's doing it. It's not weight. What are some other forces?
Normal force.
All right. What is it touching, Holly? What is one thing it's touching? The hoop. What direction would the force be from the hoop? pointing in, right? It's always a pushing force, and the hoop is on the outside. So remember, when we have a normal force, it's always a push, so the hoop pushes in on the marble. Right, let me repeat that one. There's a normal force between the hoop and the marble. That's always a push. The hoop is on the outside, so it pushes in. It would be opposite if I put the marble on the outside of the hoop, right? Now the marble is being pushed out from the hoop. Maybe we'll see if that makes it travel in a circle in a little bit. Daniel.
So you know how we, in this case, we point down, but what about the weight of the marble pushing onto the hoop? Was that what you just finished off?
Well, so we're talking about the forces acting on the marble. So it's certainly true that the marble pushes back on the hoop. How do we know that? Whose law? Whose law tells us that the marble pushes out on the hoop? Which Newton's law? Third law, right? So if the hoop pushes in on the marble, then the marble pushes out on the hoop. But we're not asking about the forces on the hoop. We're asking about the forces on the marble. Okay, so we said friction isn't going to do what we want. The weight doesn't do what we want. We've got the normal force pushing in. Is it touching anything else when I have it on the table here? Yeah, it's touching the table. What direction is the normal force from the table? Up. That's just going to cancel out the weight. So the only force we're left with that is going to accelerate our marble is a force pushing in from the hoop. Okay? So the green arrow here represents the force. It's the normal force from the ring, the outside hoop that's pushing in on the marble. If I don't have the hoop here and I try to make the marble go in a circle, I can't do it. Right? If I don't have the hoop pushing in on the marble, it will not travel in a circle. And if I take the marble and put it on the outside of the hoop and try to make it travel in a circle, well, I can't get it to do it either. If I don't have a force pushing in, it won't travel in the circle. So in the case of the marble traveling in the hoop, it's a normal force from the ring that's providing this force that points in. Always points towards the center of the circle. Okay? So again, if I move the marble to a different spot on the hoop, it's still going to be a push towards the center of the circle. I'll draw a picture of that in a second. The other thing I'll say is, in this example, I'm using a hoop to show that the force points in. But this isn't the only way you can get a force that points in to keep something traveling in a circle. Like if you took your keys on a lanyard and you spin the keys around, these keys are traveling in a circle. What's providing the force that keeps it traveling in the circle? My hand through what? Through the string. It's a pulling force. It is tension, right? You also take advantage of gravity. Gravity helps it stay in a circle. Okay, so like when you're riding a roller coaster, there's some gravity involved. If you took, for example, the moon orbiting around the Earth, gravity is providing that center pulling force. Okay. If you're driving in a car and going around a turn, it is the friction between the tires and the ground that provides the force that points in. And so lots of different forces, as long as they're pointed in the correct direction, will do thus the correct force that we need. So if there's a special name for this, that the force is pointed towards the center of the circle. And the special word is centripetal, which comes from, I believe, Greek in origin. First, and it means center seeking, right? So this force will always point towards the center of the circular path they're going in. right? Center seeking, always pointed towards the center. Now, this isn't the force that you would feel if you were on the marble, right? So sometimes you hear, oh, like things get like flung outwards. It's not that they're getting flung outwards, it's that the force isn't strong enough to keep them going in the circle. The force, as you can see, points towards the center of the circle. Right? And I'll draw another example of that. Hold on. Yeah, we've already said that. Okay. So here I have the ball at another location, right? So here the marble is at this spot over here. The velocity vector is still tangent. So it's sort of pointing like up and to the right a little bit, like so. And what direction does the force point? Inwards, right? Down and to the right a little bit, towards the center of the circle, right? And you can continue to pick other spots around the circle, and that force is always going to point towards the center of the circle, right? And that's the purpose of the hoop. The hoop is, if the hoop isn't there, what direction would how would the marble travel if there was no forces acting on it? According to Newton's first law, how would it travel? If there was no forces acting on the marble, how would the marble, what would happen to the marble's velocity? It wouldn't stop. It would have to stay constant, which means it would keep going in a straight line, because that's the only way the velocity stays the same length and the same direction. Yes.
So if you just
I'll demonstrate that on Monday.
Yeah, if you just put it on the table, won't it start rolling off the table?
Well, sure. I mean, eventually, I mean, we've talked about that. There's nowhere you can go in the universe where there are no forces, right? So we have to sort of put ourselves in this like magical land where it's possible to completely get rid of all forces. So certainly at some point, right, as Daniel pointed out, eventually, if I make the marble go around the circle, it's going to slow down because it's losing energy. In fact, you can hear the energy that it's losing. That sound comes from somewhere. That sound energy is how a lot of the energy goes away from our marble. Right? That's unit 6. So we'll talk about energy conservation when we come back in January. Okay? But the idea is that, yes, if we could go to this magical place where the only force acting on the marble was the pushing from the ring, it would continue to just go around in a circle forever and ever and ever. This is basically what the planets have been doing for billions of years. Right? No one comes along and gives them a little push every once in a while to keep the Earth orbiting around the sun. Right? For the most part, the energy has stayed the same for billions of years. Okay? Right, so on Monday, I've got in that tracker video, we'll see what happens if I take the marble and move it around the hoop and then pick up the hoop, and we'll see what happens. So that's something to think about and come in with your prediction on Monday. That'll probably be your due now, as I'll have you predict what you think is going to happen. All right, so the last thing I wanted to do before I let you try some practice questions on your own is we've got to talk about how much this acceleration is. Now, same thing, to prove this formula requires a little bit of calculus, right? Not something that we need to do for our purposes, right? But that centripetal acceleration is equal to v squared divided by r, where v is the speed and r is the radius of the circle. Right? You can already see some of the different relationships that exist, right? So let's say I like doubled the speed. What would happen to the centripetal acceleration? Let's see. All right, so Kayla, if I doubled the speed, if I made v twice as big, what would happen to the centripetal acceleration? Wouldn't just double. Why does it do more than just double? It would quadruple. Kayla, what do you notice about the v in our formula? It's squared, right? So if I double v, I'd get 4 times acceleration. If I tripled v, I'd get 9 times. If I quadrupled v, I'd get 16 times. Right? So there's a really strong dependence on v. It's a quadratic dependence. It's squared, right? So this is why it's, if you probably don't do a lot of driving, but it's why turns can be very dangerous if you go too fast in them, because you can't get enough force to keep up with the necessary acceleration, right? So it's why lots of turns will have much slower speed limits than the rest of the road around it. So like where I grew up, right, there were turns that we knew we had to slow down on because of how if you went too fast, the car couldn't do the right acceleration. Okay, Daniel.
Also has to do with things like the friction, because you know sometimes
Yeah.
you can't turn it, but what happens if you turn it too hard, the car flips, right?
Right, so that is similar. That is similar. Our other relationship is with the radius of the circle, right? So what happens to the necessary centripetal acceleration as r gets larger? What happens to it? So if I made r bigger, what happens to the centripetal acceleration? Yeah, it gets smaller. So if you make the turn radius larger, you don't need to accelerate as much. That kind of makes sense. Takes you more time to get around the turn, so you don't have to accelerate as much. A good place to feel this, the effect of the radius is when you're on the 2-3 train going into 110th Street. Right before you go into the station, right, you can usually feel that centripetal acceleration, even though the train's going pretty slow as it's pulling into the station. And the reason is there's a really sharp turn right before you come into 110th Street. So I ride that train every day, and so I'm always thinking of like the physics of that centripetal acceleration. And so when they design train tracks, that's something that they think about, making sure that the radius matches the speed that the trains are coming in at, right? And so they also will try to make the tracks as straight as possible so that they don't need to do a lot of accelerating. So like that's how like the Acela trains can run really fast from like New York to Boston, because there's like no turns. They put the tracks as straight as they could. Right. So there are some questions on not the next homework, but the one after that about this, where I'll say like what happens to a centripetal if you double this or half that. It's again, we're practicing that proportional reasoning skill. Daniel.
Also, if, okay, does this not also apply to things we have like
Absolutely. So not only does this apply to horizontal turns, but yes, this would apply to going over the top of a hill or at the bottom of a valley, right? And again, you've probably felt that before too, right? You're riding on the bus goes over the top of a hill and you feel a little bit lighter, right? You kind of go bounce up in your seat, or same thing like on a roller coaster, right? Same idea, because you're accelerating, there is a force that you need to do that.
instead of a force pushing inward, pushing outward?
Well, it's still trying to, so basically what's happening is that when you're going over the top of the turn, right, you don't need as much, your weight pulling down is not, you don't need as much force. So the normal force pointing up decreases and you feel lighter. Kind of like the elevator example, right? When the elevator was going up, you felt heavier. When the elevator is accelerating down, you feel lighter. Same idea when you're going over the top of a turn and the bottom of a turn. But the force you need is still pointed towards the center of the turn. So over the top of a hill, that points down. At the bottom of a valley, that points up. Yes, Holly?
I don't know if this is a dumb question, but if is that why some people get motion sickness?
That definitely contributes to it. So for people who like, it is definitely the accelerations like of a roller coaster that makes people feel sick. That's like different than like motion sickness, like people who read in the car, like that's different. But if you get that feeling inside of your organs like moving around and that like upsets your stomach, yes, that's absolutely because of the accelerations. All right, so let's do a calculation example of this. Right, so let's see. Vicky, read this question for us. Right, so we're just gonna go through the guess method real quick. Natalie. Natalie. All right, Landriana, give us something in the question that is given. All right, so what is that an example of? What kind of quantity did they give us? $25 meters per second is equal to what? Yep, it would be the velocity. Okay. What is another piece of given information, Metzli? All right, and how much is the radius? Okay, and what are we trying to solve for? A centripetal. So our unknown is AC. All right, now we need the equation. Daniel, what's the equation that we need?
So the centripetal center equals B squared over R.
Do we need to solve that? Do we need to do any algebra to that?
No.
No, we're all set. So we're going to plug it in.
So then B is 25 meters per second, but then squared. And then over 30 meters. I have a question.
Yes.
With the unit meters squared, would it become meters squared? Would it be meters per second squared after you square it?
You would square everything.
So meters squared second squared?
Exactly. So 25 times 25
is 625.
625, and it would, yes, be meters squared over seconds squared,
Over 30,
and I would divide it by 30 meters.
which is 20.83.
Right, and you can check to see how the units work out.
Oh, and then
This meter cancels one of these, okay, and I get meters per second squared. Pretty cool, right? So again, you definitely have to put in the units here, right? Whether you want to do the cancellation part, it's a good skill to practice. But again, if you know acceleration is supposed to be measured in meters per second squared, you can just write it down, okay? That is definitely like the most basic version, right? Where you just have to plug in V and R. Of course, you could see the question where it gives you R and A centripetal and you have to solve for V, or it might give you A centripetal and V and ask you to solve for R, right? And you just do the algebra, you move the stuff around. Nothing too crazy. Of course, the advice I always give whenever we do formulas like this, the place where people will make their mistake is with the squared. They'll either forget to square it, or at the end, let's say they needed to take the square root to solve for V, they'll forget to do it. And I promise you, if it's a multiple choice question, one of the answer choices will be leaving that out, right? So I think it's really important to write down the number with that squared. And if you find yourself struggling with that, finish doing the squared, do what Daniel did and figure out the squared number separate, right? So I recommend this when you're first getting started. Do 25 squared and write down 625, and then do 625 divided by 30, so you don't run into issues like the calculator and like forgetting. It's a silly way to not get it right, okay? Any questions about this example? It's real basic, right? So to help you practice, you can either open up My Open Math, and actually it's homework 21, so you just skip over to the next one. That's got questions about the centripetal motion stuff that we did today. We're gonna practice this more on Monday. So if you're going through these and you feel unsure, know that we will do more work on, especially drawing out the picture. That's something people have a tough time with. I think people get pretty comfortable with the formula. Or if you've already done some of these, or you want to work just with paper and pencil today, you can take the next 7 minutes of class. In the workbook, it's pages 227 to 237, have examples of some centripetal motion questions, right? So you'll work on that for the next 7 minutes. I'll be around to answer any questions that you have. I changed the deadline for the homework that was due tonight to Saturday. I recommend still working on it tonight. That way you can enjoy your break a little bit more. But thought it was fair to just give you that extra time. I'll be on my computer throughout the weekend, so if you post any questions on there, I'll definitely answer them. And definitely make sure you're checking out the website. I know I've been sending out the link in the morning. You guys asked some really, really great questions, and it's good to be able to read the answers to questions other people have as well. So if you're unsure about something from a day's class, definitely look there as well. People ask good questions. All right. So go ahead and get started, and I'll be around to answer any questions.